Hi, my name is Rashid and I'm your first speaker regarding network packet transmission monitoring system. Before we start, let's picture a scenario together, shall we? In our daily life, millions or billions of data packets transfer to the network every second, carrying a vital and a crucial information such as financial transaction, emails, or even your personal information. Have you ever thought what will happen if something goes wrong? It will be catastrophic. How do we ensure that this digital lifeline remain unbroken, secure, and efficient? Therefore, we have created a simple system to tackle this problem. But before we start, let me appreciate our lecturer and everyone that supported us and giving their hand and hard work together in this project. First and foremost, we would like to extend our heartfelt gratitude to our lecturer, Dr. Nur Haliza, for teaching us in semester 1. Throughout her teaching lesson, during physical class, we gain a lot of knowledge about digital logic, which is very helpful and useful for our future. Dr. Nur Haliza is a competent and a responsible lecturer. She was very patient teaching us. The dedication she shows is very admirable and can be an example for others. Furthermore, we like to express our gratitude to Dr. Fuad, who will allocate his valuable time to make an online explanation regarding the project. We were able to proceed with the project easily thanks to his simple explanation and clear instruction. Additionally, we would like to thank our group members for their unwavering dedication to collaborate on this final project together. To make sure this project can be submitted in time, all of our group members were very active during the discussion to make sure that we get the best solution. This is because we depended on one another and supported each other during the project.
Introduction. A transmission system refers to the methods and technologies used to transfer data from one point to another within a network or between components. This is an essential component of networks and communication system that allows data to flow effectively and consistently. We have to move a packet of data from the computer in Lab 1 to the computer in Lab 2 for our group project.
For the problem background, firstly, user need to start the system to transmit data packet from computer lab 1 to computer lab 2. The user must press the power button, turn 1 and key in their predefined 4-digit password 1001 before the device can begin to function. If the password is correct, the LED will light up and user proceed to the next step, which is selecting which computer in lab 1 to send the data to and which computer in lab 2 to receive it. When user then choose the computer, user can choose the size of data transmit between 0 to F. There will be a counter to count the number of data transmit and show the numbers on the 7-segment display. A comparator is used to compare the number of data transmit entered by the users. When the two numbers is the same, the system will stop its operation. Then, I will explain about the solution for the problem. The computer power button must be turned on. After that, users must insert a 4-digit password to proceed to the next step. A decoder is used to confirm whether the password is correct. The user cannot move on to the next step if the password they provided is incorrect. For the safety of the data, a password is essential. Once the password is correct, the LED will turn on and the user can continue to the next step. Next, the user must determine which Lab 1 computers will transmit data to Lab 2 computers. For data transmission, a multiplexer mux is used to determine which computer that will transmit the data. Meanwhile, a demultiplexer, demux, is used to select which computer that will receive the data. This add up ensures data transmission is accurate and efficient between computers in the network. The number of data transferred is then determined using three main components, which is a 4-bit counter, which is 4-bit JK positive edge counter up counter, a 4-bit comparator, and a clock enabler. The 4-bit counter is used to count the number of data transmission. The 4-bit comparator compares the number of data and the data that was transmitted. When the amount of data transmitted has reached the maximum limit, the clock enabler is turned off and the counter stops counting. Therefore, the user must enter the number of data that need to be transmitted using the data packet limiter, which allows the number between 0 and 15. For the 4-bit counter, preset and clear must set to 1. 7-segment display is connected to the count up counter to show the number of data that had been transmitted. If the number of data that had been transmitted does not meet the requirement, the system will continue to process until the values of the 4-bit counter and input switch are the same.
For the requirement, we use 4-bit decoder to verify that the password entered by the user is correct. Number 2, multiplexer to allow the user to select which computer will transmit the data in lab 1. Number 3, demultiplexer to let the user choose which computer to receive the data in lab 2. Number 4, clock enable to enable the transmission process and disable the process once the number of data transmit met the number of data transmit produced. Number 5, 4-bit comparator to compare the number of data transmit that's set by user with the number of data transmit had been produced. Number 6, 4-bit count up counter to determine the quantity of data transmission. Number 7, 7-segment display to display number of data transmit had been produced. And lastly, input 1 hex to set the maximum number of data transmit. System implementation. For decoder, we use a 4-bit decoder to create a set of password for our data transmission system. Decoder is connected to the power switch and an LED on the output, which means the decoder will only be activated when the password entered is correct, the power button is on, and then LED lights up. When the user entered the wrong password, the LED will not light up and the system could not run. The user must enter the correct password in order to activate and start to run the system. Next, multiplexer. A multiplexer is used to let the user choose which computer they want to use from lab 1 to transmit the data in lab 2. Each lab contains 8 computers. User can choose the computer from the multiplexer using a set of binary number. Then, the user need to turn on the computer and the clock to generate the data. Demultiplexer. This component is linked to the multiplexer output. It used to receive the data that has been generated to the computer in lab 2 that chose by the user. Before that, user need to choose the computer by turning on the computer and set the binary number through the multiplexer. Clock enable. The clock enabler is set up by using 5 input AND gate. The input of the AND gate contain is the signal of properties, 4-digit password from decoder, power on button, comparator, and push clock button. When these 5 input are high, the clock enabler can only be activated. The system will stop running when the number of data transmitted produced meet the number of data transmitted set by the user. 4-bit count up counter. The 4-bit counter that we use is 4-bit JK positive H count up counter. The counter start count based on the clock enabler. It will start counting if the pre and clear input are connected to high input and J and K are set as high. When the power button is activated, password entered correctly, and the clock enabler is being active, it will stop when the clock pulse is no longer received or reach the number of data transmit input by the user. 4-bit comparator. The comparator used to compare the value from 2 sources, which is the number of data transmit that have been set by the user with the number of data transmit have been produced by count up counter. This component will control the clock enabler. Once the number of data transmit produced met the value that have been set by user, the system will stop working. 7-segment display. 7-segment display is used to display the number by converting binary code received into hexadecimal. A 7-segment display is used In the count up counter, it is used to display number of data transmit that have been produced by the system.
In conclusion, our project illustrated our knowledge and proficiency in developing and constructing a network packet transmission monitoring system. We were able to accomplish our goal by adding digital components. This achievement enables us to effectively practice the concept of digital logic and is consistent with what we learned in our lectures. It was a major accomplishment to finish the circuit simulation that worked flawlessly. This attempt also allowed us regularly access the circuit system to guarantee its effective operation and provided us important lessons about enhancing digital logic design. Reminiscing our past actions, we realized that we were practicing not only practical skills but also critical thinking skill. During designing and conducting bids, we encountered many problems that led us to think twice about our mistakes. We were forced to brainstorm ideas together to tackle the problems. We were able to enhance our communicating skills and teamwork, which were crucial since the project was complex and required a plethora of decision making. As a result, the project progressed smoothly and we learned that hard work pays off. However, our system still needs myriad of improvements that can be added. For example, our system would become more dynamic and responsive with the addition of real-time data monitoring. Additionally, we can increase the scalability of the system to handle more workload and larger network environment without compromising performance. To ease network administrators' work, we can make the monitoring system's user interface more intuitive and user-friendly. By incorporating these improvements, the network packet transmission monitoring system can become more efficient and accurate while enhancing overall network performance. So this is the simulation video of our circuit. So first, we start the animation. Then, we power on one computer from lab 1, which is the source, and we enable the clock animation. And since I'm choosing the fourth computer here, I need to change the select bit at max as 0, 1, 1. After that, I need to power on one computer from lab 2, which is the destination, and I also changed the select bit as 0, 1, 1. So now, we need to fulfill the rest of the clock enabler condition.
We set the maximum byte transfer as F. After that, we power on the ready transmission switch. We set the password at decoder as 1001.
Set pre as 1 and clear as 1. Now, the count up counter initialize as 0.
We're gonna trigger the push button until the count up counter reaches F. So now, whenever we trigger the push button, the counter will count up and the output of the computer at lab 2 will blink until the counter reaches F.
Click the clear button to reset the counter. We will try to do the simulation again, but this time we're going to change the destination. We're going to choose a different computer, and we also need to change the select bit.
So now, let's do the same thing as before.
So, that was the demonstration of our circuit. We implement simplex communication and we use T flip-flop. Next, the advanced feature in our circuit was the password function as additional security. That's all from us. Thank you.